doing problem 8-4. We have a beam that is fixed at one end and has a roller on the other. And we've got 2 point loads, both distance A from the end. Here is a diagram of some of the forces. We've got A, X, and Y due to the fixed end, and just the By for the roller end. Here's the shear diagram that corresponds. We've got 2 different shears, one P and one negative P. And here's the corresponding moment diagram. And then up here we have deflection diagram. And because the beam is symmetric, we have some of the forces in the y direction are 0, and therefore AY is equal to BY, which are value P, and BX equals 0 in the x direction. We are looking for the max deflection, where the max deflection occurs, and the slope at A. Because the beam is symmetric, we can divide it in half, cut it in half, and look at only half of the beam.
Alright, so for the next part, we're supposed to find the moment equation about x1 and about x2. So we start off with x1. We're going to cut the beam here, and then you have our moment equation here. So we're going to put in p times x1, which is our moment about x1, and then take the integrate it, so we get our y prime equation, and then integrate it one more time to get our y equation. Alright, and then for the next part, it's going to be the same thing, only about x2 now. So we take our moment equation, put in our p times a for our moment, integrate it once for y prime, and then integrate it twice for our second equation. That gives us one y equation and another y equation, so 4 unknowns. And let me set up the system and solve it.
Okay, so for the next part, we have our 4 unknowns, and we need 4 boundary conditions to solve for them. For the first one, we say at x equals to 0, the deflection is equal to 0. So we take our y1, substitute 0 for x, and that gives us c2 is equal to 0. The next condition, we have continuity at point A, so the deflections are equal, so y1 of x1 equals A is the same as y2 x2 equals A. Substitute in A, and we get this equation, which gives us C1 in terms of C3 and C4. The next boundary condition is the same, continuity, except instead of using deflection, we're using the angle. So y prime 1 of x1 equals A equals y2 prime of x2 equals A. Substitute that in, and we solve C3 in terms of C1. So we need our 4th boundary condition. We have y2 prime of x2 of L over 2 is equal to 0, which says that the deflection at the midpoint, or the angle at the midpoint, is equal to 0. So plug that in, solve it. We get a term for C3, which we substitute back into here and solve for C1. We get this, which from our equation we know that the deflection y prime 1 of x equals 0 is equal to C1. So that's that. Then the other thing we were trying to find was our max deflection. We said this would occur at x equals L over 2, where our angle is 0. So plug in L over 2, solve it, simplify it, and we got this for a maximum deflection. Alright, so the very last part, you take your 6 boundary conditions and you form equations. So these, you'll have 6 equations total with 6 unknowns, and an easy way to solve it is to take the coefficients and put them in a 6 by 6 matrix, and then have that multiplied by the vector with the 6 constants of differentiation that we're trying to find, and set that equal to number likely 0. Then you just plug this into your calculator, MathCAD, whatever you want to use, and it should solve that for you. Once you have that, you'll have all 6 constants. Constants 1 through 4 should match up with what we had for 1 through 4 from our equations previously. 5 and 6 won't matter. It'll just be for that Y3 equation. So there's your check.